In this video, we're going to talk about the concept of partial pressures, specifically Dalton's law of partial pressures. It's a pretty straightforward concept. When we've got a gas, it's usually going to be a mixture of multiple gases because gases they don't have any intermolecular forces that are actually holding them together, so they just mix indiscriminately. And so let's say I've got this gas here. It's made of O2 and N2, oxygen and nitrogen gas. Well, we can see that there are 3 molecules of oxygen in this, and there's 3 molecules of nitrogen. Well, I could really consider that to be a mixture of these two separate gases. One of these gases is O2 and the other is N2. My total number of moles is going to be equal to the number of moles of O2 plus the number of moles of N2. That's pretty straightforward. That makes intuitive sense. But what doesn't necessarily make intuitive sense is this idea that this whole gas has a pressure that it's exerting on its container. And that pressure is going to be equal to the pressure that the O2 is exerting and the pressure that the N2 is exerting. So the ratio of the number of moles to the total moles is going to be the same as the pressure to the total pressure. Now let's break this up a little bit. What that means is if I want to figure out how much pressure is the O2 contributing to this, what I could do is I could set up this ratio. I could say the pressure of the O2 divided by the total pressure is going to be equal to the number of moles of O2 divided by my total moles. So let's just say this is 6 moles, just to keep things nice and simple. Say that's 6. And we'll say that this is 3, and we'll say it's at an atmosphere, let's go 10 atmospheres. 10 atmospheres. Now I want to know how much pressure is that O2 actually exerting? Well, I can just place those numbers in this ratio here. I can say there's 6 total moles divided by the 3 moles of O2, and I've got 10 atmospheres of pressure for my total pressure, and then I want to know what is the pressure of the O2. Well, that's a pretty simple ratio. 3 divided by 6, it's going to be 0.5 times 10, it's going to be 5. So this is going to equal 5. 5 atmospheres of pressure is being exerted by that O2. And then I could easily figure out how much pressure is being exerted by the nitrogen. Well, that would just be 10. It would be 10 equals 5 plus, well, what would this be? It would have to be 5. Straightforward, right? This is a very straightforward relationship between these. But the concept of partial pressures is not always intuitive. Like, wait, why do we care? Why do we care about partial pressures? And there's actually several decent uses for partial pressures. It can help us understand how much of a certain gas there is in a mixture of gases. For example, we might want to be collecting chlorine gas for some other chemistry that we want to do later on. We need to know how much chlorine gas there actually is. In addition, there are going to be a lot of times where we collect gas over water, and water is going to exert a constant partial pressure depending on the temperature. And we'll look at that in just a sec. But let's get a little more practice with this. Let's say I've got this mixture of 3 gases. I've got nitrogen, hydrogen, and oxygen. And I've got 5 moles of nitrogen, 2 moles of hydrogen, 9 moles of oxygen, and I've got a total pressure of 15 atmospheres. And I want to know what is my partial pressure of each one of these. Let's go ahead and let's make this a little table. So I've got the number of moles, and then I want to know the pressure of each one of these. So what's going to be my total number of moles? Well, for that, I'm just going to do that. It's very simple. It's just going to be the number of each of those moles added together. So it's just going to be 5 plus 2 plus 9, which is going to be 16. Right? So my total number of moles is 16. And so now I can easily figure out the partial pressure of each of these gases by going, all right, I want to know the pressure. Let's start with N2. The pressure of N2 divided by the total pressure will be equal to the number of moles of N2 divided by my total number of moles. So that's going to be that partial pressure divided by total pressure, which is 15 atmospheres, equals, and then my number of moles for nitrogen is 5 divided by my total number of moles, which is 16. Now we can just rearrange this. We can multiply both sides by 15 to get that pressure on its own. Great, and then let's calculate. We get 4.6, 4.7. So my partial pressure of N2 is 4.7 atmospheres. Next one, H2. Let's do that one as well. That's going to be pressure of H2 divided by the total pressure of 15. It's going to be equal to that same ratio of the number of moles, which is going to be 2 divided by 16. 2 divided by 16 times 15. We're going to get 1.875. So let's just call that an even 1.9. It's going to be 1.9 atmospheres. And then lastly, the O2. We're going to have pressure of O2 divided by 15 equals number of moles of O2 divided by the total number of moles. So 9 divided by 16 times 15. Just some simple algebra here. So that's going to be 8.4. And there we go. So that's just a quick sample problem, just showing these relationships. This is not too hard of a concept to do mathematically. Remember, it's just going to be that NT equals N1 equals N2. And it doesn't matter how many gases we have. We could have 50 gases, and it's still just going to be the addition of all of those gases. Okay? Same with the partial pressures. It does not matter how many, it's just going to be the addition of all of them, and then it's just going to be that relationship, the relationship between those ratios here. So now, let's look at another way that we can use partial pressures. This is going to be something like when I'm trying to do a reaction where I'm collecting a gas. Let's say I'm collecting a gas. Let's say I've got this reaction where I'm mixing some zinc and some HCl, some zinc with some HCl. And that reaction will produce hydrogen gas. Let's say I want to isolate that hydrogen gas. I don't want to just mix into the atmosphere. So I'm gonna run it through a tube. I'm gonna put it into an inverted beaker, or an inverted test tube that I started out with, filled with water. And so this is a pretty common practice. We collect gases over water, because as that gas flows in here, it'll push the water down, and then I'll be left with just a pure gas. So in there, that would be pure H2, and I don't have to worry about it being mixed with the atmosphere at all, which is, there's various reasons why that might be necessary, right? H2 is combustible. I don't want it mixed with any oxygen. I don't want there to be any oxygen there. But we do have a problem with this, because depending on the temperature, that water will exert a vapor pressure. We call this a vapor pressure, where some of that H2O will become a gas. Just naturally. It just naturally does this. This is why water evaporates before its boiling point. Just a bright sunny day, it'll evaporate off of the sidewalk because it's exerting a vapor pressure. Some of that water is turning into a gas, and it's going to exert an exact partial pressure based on the temperature. So let's say I'm collecting this hydrogen, and let's just say it's at 5 atmospheres of pressure. And let's say we're doing this at, let's say it's a pretty hot day out. Let's say it's 30 degrees. So I'm going to look on this chart here. This chart has all the vapor pressures of water at different temperatures. So let's say it's 30 degrees out. Well, what is my atmospheric pressure going to be from that water? Well, it's going to be 0.0419. So if I want to know what's my partial pressure of hydrogen here, I can go, it's going to be total pressure. It's the pressure of the H2 plus the pressure of the H2O. So it's going to be 5 equals the pressure of the H2, which is what I'm looking for, plus that partial pressure of H2O, which is 0.0419 in this case. So I just do that simple subtraction. And I get 4.96. We'll round to 4.96. So 4.96 atmospheres of H2. Okay? And then we could use Dalton's law of partial pressures to actually calculate how many moles of H2 would I have in there. So this is where this becomes pretty useful. It's pretty necessary to figure out exactly how much of that gas do I have. And so when we do this type of calculation, we say how much dry gas is there, which is how much gas is there if we remove the water. So we need to figure out the partial pressure of that water vapor, and then we need to figure out how to remove it. Okay? So these are the two simple calculations you'll be able to do on partial pressures is we'll be able to look up in a table what's the partial pressure of that water vapor at that temperature, subtract that to figure out what's my partial pressure of other stuff, and then we'll be able to figure out these ratios just based on the number of moles of different gases I have, what is going to be my partial pressures of each of those gases.